Hi, I'm Brendan Collins, co-founder and principal at makepath. Me, my co-founder Pablo Fuentes, and the makepath team are proud to be part of the Texas GIS community and super excited to participate in and sponsor ATX GIS Day. Big thank you to the ATX GIS Day committee, organizers, and attendees for making such an event possible and for promoting GIS within our fine state. GIS and data science communities are thriving in Austin. Institutions including the University of Texas, St. Edwards, and the Austin Community College are advancing the field of spatial data science and delivering world-class curriculum, while private companies like Anaconda, Quansight, OpenTeams, and MakePath are finding robust models to fund development of next-generation free and open source tools for spatial data science and AI. At MakePath, we specialize in spatial data science services and are experts in all things GIS. In addition to wielding the proprietary and popular GIS tools we all know and love, like ArcGIS Desktop and ArcGIS Server, we are very active in the open source community and have developed a fast, accurate, Python-based raster analysis library called Xray Spatial. Today, I'm going to be introducing a few of our favorite open source tools which can augment your spatial analysis capabilities. All of the tools are free to download and are welcome to contributions. Let's get started with the question, why is open source software important and what are the benefits for public and private entities? Here are 5 major reasons why considering open source tooling is important. First and foremost, the use of free and open source tools lowers total ownership costs by eliminating license fees. This means more of your staff can access cutting edge tools while also eliminating line items in your budget. Secondly, you can extend open source tools for your specific use cases. If you're implementing a super custom analysis, say for ecosystem fragmentation or flood management, you can open source your scripts and collaborate with other groups working on similar projects who can improve upon your work. This reduces redundancies and lowers overall cost of tool development and maintenance. As the famous Linus Torvalds once said, given enough eyes, all software bugs are shallow. When you use open source tools, there's a level of transparency into the code which can help ensure accuracy. You can also suggest enhancements and contribute bug fixes and documentation. Fourth, scaling an analysis to large problems can be easier with open source tools because you don't need to license individual machines. You can validate an analysis using a single workstation and then scale it to hundreds of machines without needing to connect to a centralized license server, which can be a bottleneck and also a single point of failure. Lastly, when you participate in open source and use open source, you join a larger community centered around a common mission. GeoPandas, Datashader, QGIS, Xray Spatial, Hadoop, Spark, Dask, Hive, and many other big data tools began and continue as open source projects. These projects many times have corporate and academic sponsors who share the burden of maintenance and support. When you participate in these ecosystems, you can get connected with interesting people in different areas and different domains, which can be an asset as you explore and innovate. Let's dive a little deeper now and look at 2 projects which are particularly important to the GIS community. The first is the Python programming language. Python's motto is programming for everyone. Designed as a language for teaching programming to children, Python is approachable and chances are you've already run across it while using other GIS packages like ArcGIS Desktop or QGIS. Python has blossomed over the past decade to be the dominant language for data science, machine learning, and web development. When you learn Python for GIS, those skills are also transferable into these other areas. Analysts and developers flock to Python because of its simple syntax and rich ecosystem of available packages. In a world of technologies which require time to learn, Python has a great return on investment. Another project to highlight is Project Jupyter. Project Jupyter produced the Jupyter Notebook and Jupyter Lab tools, which are staples for the data science community. The Jupyter Notebook is an open source web application that allows you to create and share documents that contain live code, equations, visualizations, and narrative text. Uses include data cleaning and transformation, numerical simulation, statistical modeling, data visualization, machine learning, and much more. Let's take a closer look at how we at MakePath combine these tools together. Let's take a few minutes to see Python and Jupyter in action. Here we're looking at a Jupyter notebook which aims at identifying pharmacy deserts in the lower 48 United States. What's important here is seeing that we're combining text and executable code with intermediate outputs, all within the web browser. So in this single file, we can encapsulate everything that a colleague needs to reproduce our analysis. After defining our study area, we look at pharmacy deserts by calculating first the distance to the nearest pharmacy, classified using natural breaks, finding block groups with particularly high percentages of residents over the age of 65. We intersect those two rasters to highlight those areas that are particularly far away from pharmacies and also include a lot of residents over 65 years old. We summarize that raster using zonal statistics, and that gives us our top 10 lower 48 counties with particularly high percentages of pharmacy desert. A nice thing about these notebooks is that you're able to export any of these outputs as a standard image file. It might be a JPEG or a PNGs to be included in PowerPoint presentations. In our case, we decided to communicate the results of our analysis as a blog post. Here on the MakePath blog, we talk about our methodology in finding these pharmacy deserts and can include these graphics right out of the Jupyter notebook. But we don't stop at a blog post. We provide a link to the notebook so that folks can reproduce our analysis and also use the notebook as a template for running their own analyses with their own analysis questions. Again, we used Datashader and Xarray-Spatial as our analysis tools in calculating pharmacy deserts. And let's take a sec to look at some of the other tools that are available inside of Xray-Spatial. Xray-Spatial is a raster-based spatial analysis library for Python. Here, we're looking at the Xray-Spatial GitHub repository, which contains all the code and documentation for the project. Here we can see open issues. These may include enhancements or bug fixes, pull requests, which are contributions from the larger community, and also our project board, which can show some of the roadmap for new features that will be added in the coming quarter. Taking a look at some of the tools available within the library, we see surface analysis tools like slope, aspect, curvature, and hillshade, multispectral tools like NDVI, and then other analysis tools like focal statistics, zonal statistics, viewshed analysis, proximity analysis, and also pathfinding. We see some examples of how to use these tools, and also some additional resources like Xray-Spatial YouTube videos and example maps that were created using Xray-Spatial. One of the ways that I judge an open source project is one, by the number of stars it has, and also by the number of contributors and releases. Xray-Spatial is somewhat young, but we have contributors from many different industries and regions, which means that Xray-Spatial will be supported into the future because there are many different devs in different areas making contributions. Looking at the examples directory, we can see the Xray-Spatial user guide, which shows some of these tools in action. This is a Jupyter notebook, which is rendered inside of GitHub, so you don't have to download it, and we can see some of the tools that are available. Here we're looking at the proximity notebook, where we can see a couple of different points, and we're going to calculate a proximity grid for the distance to the nearest point. So this shows how to use Xray-Spatial to create this Euclidean distance grid, and can be used as a good starting place for your own analysis. We invite you to become a contributor to Xray-Spatial and that may include helping with documentation or simply testing out the tools on some of your own projects. In wrapping up, we'd like to highlight that open source tools are often framed in opposition to proprietary tools like ArcGIS Desktop and ArcGIS Pro. We urge you to avoid this framing. Xray in particular has made massive contributions to the open source community, including the shapefile specification, open file geodatabase specification, and are a major contributor to free and open source software projects. To help folks learn more about open source GIS and the history of open source GIS, we recently created an interactive infographic showing some of our favorite projects. This infographic details the release dates, contributors, as well as links to learn more about each specific project. Thank you to the ATX GIS Day Committee, Texas A&M University, and all the participants in this year's event. We are happy to connect with any of you who have questions or would like to learn more about what we do at MakePath. Thanks again and enjoy the rest of ATX GIS Day.